Whoops, that's not going to work.
All right, now. There we go. All right, so I've already covered everything I need to for the next exam on Tuesday. So a little bit ahead. So I'm going to start 11.1, and we'll see how it goes. Okay, so I'll try to do 11.1, and I'll try to leave you time for questions and answers. Because the more questions and answers I take care of today, the fewer I have to take care of on Tuesday. Okay, so next test is Tuesday. No quiz today. Let's make it, there's a bogus quiz today, and everybody automatically gets 5 points on it. How's that? Okay, so you all get 5 points for doing nothing on a quiz. All right. So coverage is right here. Bring your polar graph paper. So I will for sure have you do 1. I don't know if I'll have you do 2, but minimum 1. You might want to bring 2 just in case you mess up. If you're like me, I mess up sometimes. So bring the polar graph paper. It has to be the Melvin Hom approved polar graph paper, not your own. So I can grade everybody the same for uniformity. It has 14 circles, so you know how to break up the 14 circles. So bring the polar graph paper. There's definitely going to be 1 question from each section and maybe a couple or even 3. I mean, for 10.5, there was a parabola, ellipse, and hyperbola, so I'm very likely to ask you 1 of each minimum. So maybe 3 questions from here. And so that might take 1 away from one of the others. But some of the others, maybe it's only good to give 1, like a sketch, a curved sketch, polar graph paper, something like that. Okay. All right, so I'll get started with 11.1. So my game plan is 11.1 minimum today. And we're on to our last chapter, although it's a large last chapter. Okay, so I'll do 11.1, but I'll leave you some time for questions and answers in preparation for the test. Tuesday, I'll lecture a while, maybe 11.2. Then let you ask questions, and when that's done, we'll break it and take the test. So again, like the last couple of times, if we want to start the test early, that's all up to you. The latest I'll start is what, 8:35, which means we have to end the first half by 8:25. But you know, if we stop earlier, that's fine by me. Okay. All right, so here we go, 11.1. Okay, 11.1 is on sequences. You may have had sequences before, page 694. A sequence can be thought of just as a list of numbers written in order. Okay, we call it A1, A2, A3, A4 in general, AN. Okay, so A1 is the first term, A2 is the second term, AN is the nth term in general, and so on. Okay, so we can write them all out like this, or you can also write it like this, A sub n. This is a sequence, just an ordered list of numbers. Okay? Quite often we will have a rule attached to them. Okay, so like this, A sub n equals n over n plus 1. Okay? Or you can write it like this, n over n plus 1 is n equals 1 to infinity. For the most part, our sequences are going to go on forever. So they're not going to be finite where they stop after a while. They go on forever. Okay, so you would just plug in. Plug in 1, you get 1 over 2. Plug in 2, 2 over 3. Plug in 3, 3 over 4, and so on. Right? So you can find any term. What's the 1 millionth term? Just plug in 1 million. A million over 1,000,001. Right? And here's another such sequence. We will see this concept quite a bit. Negative 1 to the nth power, or maybe to the n plus 1 or n minus 1. Okay, negative 1 to the first power is negative 1. Negative 1 squared is positive 1. Negative 1 cubed is negative 1. Negative 1 to the fourth is positive 1. You see what that does? It makes it alternate between minus, plus, and so on. Okay, we'll call this kind of sequence alternating. We'll use the word alternating quite a bit for the rest of this chapter. So alternating, right? Plus, minus, plus, minus, plus, minus. Starting with either a positive or a minus, and then it just alternates. So one way to make it alternating is with negative 1 to the n, or maybe to the n plus 1 or n minus 1. Okay, so you can just come up with a rule, and then you can find any term in the sequence that you want, right, based on that. Okay, so that's not that big a deal. So those are sequences. Sequence can have a limit. So as n approaches infinity, do the terms approach any number, or they might approach infinity, or they might approach negative infinity. Okay? All right, if we approach a number, we say the sequence is convergent, or the sequence converges. Okay, so converges, convergent, converge, if we approach a real number. If we do not approach a real number, we say the sequence diverges or is divergent. Okay, I will abbreviate convergent with C, diverges, divergent with D. Okay, now diverges could mean goes to infinity or negative infinity, but it doesn't have to. It just means you don't approach any one number. Okay, so we take the limit as n approaches infinity quite often. Okay, so we get a real number, sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. Okay. All right. So little bit of language, but this pretty much mirrors what happens for functions. A sequence can be increasing or decreasing, right? A sub n is less than a sub n plus 1. That means for each successive term, it's going higher, increasing. Reverse it, decreasing. Right? It's always going down. A sub n is greater than a sub n plus 1 for all n greater than or equal to 1. Then we say a sequence is monotonic if it's either increasing or decreasing. So that means it's all the time going up or all the time going down. That's called monotonic. Okay, a little bit more language. Page 701, that was page 700, the monotonic stuff. Okay, 701. A sequence is bounded above if there's a number m such that a sub n is less than or equal to m for all n greater than or equal to 1. Okay, bounded above means there is a real number which is greater than or equal to all the terms of the sequence. You can be bounded below. If there's a number little m, so notice big M, you know, for big number, I suppose. Little m for smaller number, minimum number. Okay, bounded below if there's a number little m such that m is less than or equal to a sub n for all n greater than or equal to 1. Okay, and then if you have a sequence which is bounded above and below both, then we just say it's a bounded sequence. Okay, and we'll see examples of all of these things. Okay, so bounded above, let's say all the terms are less than or equal to 10. Okay, bounded below, all the terms are greater than or equal to, say, 0. And if both are true, then we just say it's bounded, period. Okay. All right, so that's that. And we're ready to start some of the problems. And again, my problems on the homework may not match yours, but again, we know what's happening. Okay, now, list the first 5 terms of a sequence. That should be very easy. They give you a rule, you just plug in 1, 2, 3, 4, and 5, and that's the basic idea, right? Okay, so 11.1 is the homework. Of course, this will not be covered on next Tuesday's exam. This is going to be for our last exam. Okay. So 11.1, again, don't be surprised if my numbers don't match yours. You're still learning the stuff. Okay, so I might peek over once in a while and see if it's the same. This one does not appear to be the same. It's close, but not quite. But anyway, a sub n is 2n over n squared plus 1. So it says list the first 5 terms of the sequence. No big deal. Plug in 1, 2, 3, 4, and 5. Plug in 1, 2 over 1 plus 1 is 2. Plug in 2. 2 times 2 is 4. 2 squared plus 1 is 5. Plug in 3. 2 times 3 is 6. 3 squared, 9 plus 1 is 10. Plug in 4. 2 times 4 is 8. 4 squared, 16 plus 1 is 17. Plug in 5. 2 times 5 is 10. 5 squared plus 1 is 26. And reduce. So if I reduce all these, it's 1 4/5, 3/5, 8 over 17, 5/13. Very easy, right? You just plug in 1, 2, 3, 4, and 5. Dot, dot, dot. Dot, dot, dot means it keeps going. They just ask for the first 5. Okay, in general, these sequences are infinite. They go on forever. And you can find any term that you want. So what is the 100th term? Plug in 100. What is the millionth term? Plug in a million. Right? Okay, my number 5, a sub n equals -1 to the n minus 1 over 5 to the n. Okay, let's think again about plugging in here. So if I plug in 1, I have -1 to the 0, which is 1. If I plug in 2, I got -1 to the first power, which is -1. If I plug in 3, I have -1 squared, which is 1. If I plug in 4, I have -1 cubed, which is -1. So it makes it alternate with the first term being positive. Okay, so positive, negative, positive, negative. So the -1 to an exponent, either to the n or n plus 1 or n minus 1, makes the sequence alternating. And you can make it so that the first term is positive or the first term is negative by putting in n or n plus 1 or n minus 1, right? And then 5 to the n, 5 to the first, 5 squared, 5 cubed, 5 to the fourth, 5 to the fifth, and so on. Okay, so no big deal at all, I hope. Okay, my number 7 has the exclamation point, which is factorial. So let me review for you the idea of factorial. I'm sure you've all seen factorial before. N exclamation point, n factorial. It's defined only for whole numbers, 0, 1, 2, 3, and so on. Okay, so you can't have a fraction, you can't have pi, you can't have negatives. So there's no such thing as -1 factorial. There's no such thing as pi factorial. There's no such thing as 1.5 factorial. Okay, starts with 0. All right, 0 factorial is 1 by definition. It's 1 because we said so, okay, although that's a very good definition, actually. Okay, 1 factorial is also 1 because we said so. So not very interesting yet. The factorial gets more interesting starting with 2. So for n greater than or equal to 2, n factorial is either 1 times 2 times 3 all the way up to n, or you can start at the top, n times n minus 1 times n minus 2, and work your way down to 1. So for instance, 2 factorial is 1 times 2, 2. 3 factorial, 1 times 2 times 3, 6. 4 factorial, 1 times 2 times 3 times 4, 24. 5 factorial, 1 times 2 times 3 times 4 times 5, 120. 6 factorial, 1 times 2 times 3 times 4 times 5 times 6, 720. You say, do I have to memorize these? Not really. It's nice if you have them memorized, okay? But if you don't, you can always derive them. I happen to have it memorized because, you know, I see this all the time. So up to 6 factorial, it's nice to know 1, 2, 6, 24, 120, 720. After that, it's probably not worth it. Okay, and also, yes, 6 factorial, you can also think of it as 6 times 4, 5 times 4 times 3 times 2 times 1. So that also works. Okay. All right, so this is a factorial. So now for 7, or more accurately, my 7, a sub n is 1 over n plus 1 factorial. Right, write the first 5 terms. So I plug in 1, 1 over 2 factorial. Plug in 2, 1 over 3 factorial. Plug in 3, 1 over 4 factorial, 5 factorial, 6 factorial. Okay, and then I just copy these guys over here. So it's 1/2, 1/6, 1/24, 1 over 120, 1 over 720. As you probably notice, the factorial grows very quickly, right? This thing grows very fast, which may be the reason why they use factorial, like, you know, shocking or something, you know, surprise. It grows extremely fast. It's one of the fastest growing functions that are out there. Okay. And even though they grow pretty fast, there are some problems which are not that hard to do when you take ratios. Okay, so I'm making some feeble attempt to try to cover this up. Okay, 10 factorial is pretty big. 9 factorial is pretty big. I claim you can do this in your head. Okay, can you see how to do this? Think of the definition, 10 factorial divided by 9 factorial. Okay, the answer is 10. Because what's 10 factorial? 1 times 2 times 3, dot, 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 times 9 times 10. 9 factorial is 1 times 2 times 3, dot, 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 up to 9. All of these cancel all of these, so you're left with just 10. Okay. So I don't know what 10 factorial is, big number. I don't know what 9 factorial is, big number, but the ratio is definitely 10. See that? Okay, another example, suppose the number on the bottom is bigger. 6 factorial over 8 factorial. Okay. I claim you can do that in your head. 6 factorial, 1 times 2 times 3 times 4 times 5 times 6. 8 factorial has those exact same numbers, 1 through 6, but also 7 and 8, right? And these cancel these out, so 1 over 56. Is that right? Okay, we're going to do a lot of stuff like this later on. Can you tell me n plus 1 factorial divided by n factorial? Okay, way to think of it is, okay, which has more factors, the top or the bottom, and how many more? Okay, that's always a good analysis. Like over here, right, I would say, which has more, the top or the bottom, and how many more? So, oh, the top has 1 more. Or what does the top have that the bottom doesn't have? 10. All the rest match. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. They cancel out, so there's a 10. This one, I say to myself, okay, the bottom has more. How many more? 2 more. What does the bottom have that the top doesn't? 7 and 8. Right? They both share 1, 2, 3, 4, 5, 6. 1 times 2 to 3, 4, 5, 6. 7, 8 extra. Okay, so for this one, which has more, the top or the bottom, and how many more? Top has 1 more, n plus 1. So the answer is n plus 1. Okay? Because this is the bottom is 1 times 2 times 3, dot, 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 up to n. This is 1 times 2 times 3, dot, 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 times n. They would all cancel out. And then there's an extra n plus 1. So this is equal to n plus 1. Okay. How about this one? n minus 1 factorial divided by n plus 1 factorial. Can you work that out? Okay, and a way to think of that is which has more, the top or the bottom? And then how many more? Or say to yourself, what does the bottom have that the top doesn't, or vice versa? Can you figure that out? So first, which has more, top or bottom? Bottom. How many more? 2 more. N and n plus 1. Okay. This is 1 times 2 times 3 times n minus 1. The bottom is 1 times 2 times 3, etc., times n minus 1 times n plus 1. So all of these guys will cancel out. So the answer is 1 over n times n plus 1. Okay, get the idea? We're actually not doing a whole bunch of these right now, but we'll see this later. So I'm introducing it to you right now. Okay, my problem 9 is a recursive definition. So they don't give you a rule like over here, any of these, okay? But they tell you the first term, and then they tell you, given any term, how do you get the term after that? So A1 is 1, you have to start somewhere, and then A sub n plus 1 equals 5A sub n minus 3. So this is a recursive definition, and maybe you computer science people know something about recursion, a recursive definition. So it's not written like this, but you're given the first one, and given any term A sub n, you can find A sub n plus 1. So that means if I have the first term, I can plug in here to find the second term. And then once you have the second term, you can plug in to find the third term. But once you have the third term, you can find the fourth term, so you can find any term that you want. Okay. Big drawback is you can't jump straight to any one term. Like over here, right? If I say, what is the 1 millionth term? I just plug in 1 million. Okay. Unfortunately, for recursive definition, unless there's something nice about it, there's a pattern that you can figure out. The only way you can get the 1/1,000,000th term is to literally go through all of them. Okay, you'd have to go through the first term is 1, whatever. Then you'd have to figure out the second, the third, and fourth. Of course, that's too much for you and me to do, but that's easy for a computer to do, to go run this algorithm 1,000,000 times, right, and so forth. Okay, so A2 is 5A1 minus 3, right? So I put 1 here. 1 plus 1 is 2. So how do I find the second term? 5A1 minus 3. So that's 5 times 1 minus 3, which is 2. Keep doing that. How do I find A3? It's 5A2 minus 3. So 5 times 2 minus 3 is 7. In other words, I just keep going 5 times the number minus 3. So the next one is 5 times 7 minus 3, 32. A sub 4, get the idea? Then how do I find A5? I plug in 32 here. So it's 5 times 32 minus 3, 157. So here are the first 5 terms. But notice I could not just jump straight to the 5th term. I had to go one by one. Okay, how do I get the second term? I plug in here. And now that I have A2, I can plug in to find A3. And now that I have A3, I can plug in to find A4, and so on. So this is a recursive definition. Okay. All right, and again, a sequence converges if the limit as n approaches infinity of a sub n exists as a real number. Okay. Otherwise, we say that the sequence diverges. Okay. It could diverge to infinity. It could diverge to negative infinity, or it might not approach anything. It doesn't matter. All those instances, we would say the sequence diverges. Okay, so now there's a bunch of problems. Again, they may not match yours, but you're still learning how to do stuff. Okay, so does the sequence converge or diverge? Okay, so a sub n is 1 minus 0.2 to the n power. Okay, so I'm basically finding the limit as n approaches infinity. Okay, so if I plug in 1, I get 1 minus 0.2, which is 0.8. If I plug in 2, I have 1 minus 0.2 squared, that's 0.96. If I plug in 3, it's 1 minus 0.2 cubed, which is 0.992. And you can kind of tell right away this is approaching 1. Okay, like a nice way to think of it is if n gets bigger and bigger, okay, plug in 1,000,000. 0.2 to the million, 0.2 times 0.2 times 0.2 times 0.2 is really, really, really small. That approaches 0. So in the limit, I would have 1 minus 0, which is 1. Okay. Okay, my 25, a sub n equals 3 plus 5n squared over n plus n squared. Okay, so there's a trick you can do in Calc 1, I think. This is n squared, this is n squared. You divide top and bottom by n squared. See how I go 3 plus 5n squared over n plus n squared, divide top and bottom by n squared. So this becomes limit as n approaches infinity. 3 divided by n squared plus 5n squared divided by n squared is just 5. Divided by n over n squared is 1 over n. N squared over n squared is 1. Okay, and now you can tell when n gets super big, this approaches 0, this approaches 0. So I have 5 over 1, which is 5. Okay, so we had that. Another bit of intuition. This is second degree. This is second degree. So for super big n, it's like these drop into insignificance. Right? You just kind of forget about the 3 and the n and say 5n squared divided by n squared, 5. Okay, still another way you can do this is L'Hopital's rule. Did you have L'Hopital's rule in Calc 1? Okay, so if limit as x approaches a, or plus or minus infinity, of f of x over g of x yields 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Okay, so in other words, over here, this is type infinity over infinity. If I plug in a super big number, the top goes to infinity, the bottom goes to infinity. So L'Hopital's rule applies. You can differentiate the top and bottom. This would be 10n over 1 plus 2n. That's again infinity over infinity. So I can do L'Hopital's rule again. So derivative of the top and the bottom, 10 over 2. So that's fine. Okay, 31, a sub n is n squared over radical n cubed plus 4n. Now, a little bit of intuition. Can you get a feeling of what's going to happen? For super big N, forget about that, right? So this is essentially n to the 3/2. This is n squared. N squared is going to win in the long run over n to the 3/2. So we think this limit should be infinity. Okay, now how do I prove it? I divide top and bottom by n to the 3/2, which is what we think this is essentially. For super big N, this is like n cubed. So I divide the top by n to the 3/2, and please look at this. I'm dividing the bottom by n to the 3/2, which means put n cubed underneath the square root. Okay, so because this is underneath the square root, when I write this, I'm really doing n to the 3/2. So this is legitimate, the stuff in red. Okay, now n squared over n to the 3/2 is n to the 1/2 over radical n cubed over n cubed is 1 plus 4 over n squared. And that means radical n over radical 1 plus 4 over n squared. Okay, now when it's like this, you can tell what happens in the limit. So limit as n approaches infinity. The bottom, 1 plus 4 over n squared, sorry, you may not be able to read it. It's the same as that. That approaches 1. Right? When n is super big, that approaches 0. The bottom is 1, but the top goes to infinity. Okay? So the limit is infinity. And yes, that means the sequence diverges. Okay, so sequence diverges in this case. Okay. Okay, speaking of 37, just talked about that. Okay, when we write it like that, that's still a sub n equals blah, 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 right? 2n minus 1 factorial over 2n plus 1 factorial. Okay, so which has more factors, the top or the bottom? And how many more, right? The bottom has more. What does the bottom have that the top doesn't have? 2n and 2n plus 1. Because this is 1 times 2 times 3 times dot, 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 2n minus 1. The bottom also has 1 times 2 times 3 times dot, 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 2n minus 1. And then the next one is 2n. And the next one is 2n plus 1. So this simplifies to this. All right, and that's easy. Limit as n approaches infinity of this is 0. The bottom gets big, the top is 1. Limit is 0. Okay, 35. A sub n equals cosine of n over 2. Well, cosine 1 over 2, cosine 2 over 2, 3 over 2, 4 over 2, 5 over 2. Okay. Well, you know the way the cosine goes. Cosine bounces up and down between -1 and 1. We never approach any one number. So this sequence diverges. Okay. We're not saying it diverges to infinity or negative infinity. In fact, this is a bounded set. It's bounded between -1 and +1, as we know. Okay. Or just think of the graph of cosine, right? Cosine bounces up and down. It's stuck between -1 and 1. So this is an example of a bounded set, but it doesn't converge. It diverges. Okay, 41. N squared e to the -n. Okay, so what's the limit? Okay, the best way to do this is to put the e to the n in the denominator. Limit as n approaches infinity of n squared over e to the n. Okay, this is infinity over infinity. When n is big, n squared is big, e to the n is big. Infinity over infinity, I could do L'Hopital's rule. Okay, so again, what's L'Hopital's rule? If the limit of a quotient gives you either 0 over 0 or infinity over infinity, take the derivative of the top and the derivative of the bottom, and you get the same limit. Okay, word of caution, do not do the quotient rule. You might recall you don't do the quotient rule for L'Hopital's rule. Just take the derivative of the top and the derivative of the bottom. So derivative of the top 2n, derivative of e to the n is still e to the n. Okay, this is still infinity over infinity. When n gets big, that's big, that's big. Do it one more time. Derivative of the top is 2. Derivative of the bottom is e to the n. Okay, and now you can tell that this limit is 0. All right, when n gets super big, 2 divided by super big is practically nothing. Okay, 43, and again, my 43. And my 43 is actually the same as your 43 this time, at least. A sub n is cosine squared of n over 2 to the n power. Okay, now it's hard to get a hold of cosine n or cosine squared of n, but I know it's stuck between 0 and 1. Okay, so I'm going to be doing something called the Squeeze Theorem. Okay, do you remember something called the Squeeze Theorem from Calc 1? Okay, so here's the idea. Do you agree with this? 0 less than or equal to cosine squared of n less than or equal to 1. Now, cosine is stuck between negative 1 and 1. Cosine squared, well, it can no longer be negative, so it's stuck between 0 and 1. Right? Agree with this? And then I divide all 3 sides by 2 to the n, which is positive. So I now have 0 less than or equal to cosine squared of n over 2 to the n, less than or equal to 1 over 2 to the n. Okay. And you may recall the idea behind the squeeze theorem. Okay. I take the limit of this function as n goes infinity. I take the limit of this function as n goes infinity. If they approach the same limit, then any function that's stuck between those two also approaches the same limit. Okay, so lower function, upper function. What's the limit as n approaches infinity of 0? Well, 0. What's the limit as n approaches infinity of 1 over 2 to the n? All right, 1 over 2 to the 100, 1 over 2 to the 1,000, 1 over 2 to the million. That approaches 0. So therefore, by the squeeze theorem, the function that's in between them also has to approach 0. Okay, so this is a true statement. Cosine squared of n over 2 to the n is stuck between 0 and 1 over 2 to the n. Okay. This thing approaches 0. In fact, it's always 0 as n goes infinity. This thing approaches 0 as n goes infinity. This is stuck between the two. It's squeezed in, so it also approaches 0. Okay, so that's something called the squeeze theorem. Okay, 45 is kind of interesting, and I think this one matches, yes. A sub n is n sine of 1 over n. I want to use L'Hopital's rule, but there has to be a fraction. I force it to be a fraction, like this. Okay, so multiplying by n is the same as dividing by 1 over n. Okay, do you agree? Divide by 1 over n, multiply by n over 1. Now I take the limit as n approaches infinity of this. This is 0 over 0. Okay, when n gets big, 1 over n approaches 0. That approaches 0, sine of 0 is 0. So I can do L'Hopital's rule. So limit n approaches infinity. The derivative of sine of 1 over n is cosine 1 over n times the derivative of 1 over n. I could work it out, but I don't have to. Let me just write it as 1 over n prime. By L'Hopital's rule, I'm supposed to differentiate the bottom. 1 over n prime. 1 over n prime cancels. Yes, you could make that what? N to the negative 1, whose derivative will be negative n to the negative 2, and then they would just cancel out. Okay, but you can cancel 1 over n prime, 1 over n prime. And now I can do this. So when n gets super big, I have cosine of 0. Cosine of 0 is 1. Okay, 47. Let me see if it matches this one. Yeah, this one even matches. A sub n is 1 plus 2 over n to the n power. Okay, so you have to do a little trick for this one. Okay, first, I'm going to let y be 1 plus 2 over n to the n. So I'm really trying to find the limit as n approaches infinity of a sub n, or limit as n approaches infinity of y. Limit as n approaches infinity of 1 plus 2 over n to the n. Okay, so what I'm going to do is take the natural log of both sides. ln of y is equal to ln of 1 plus 2 over n to the n. The reason why I do that is now I'm allowed to bring that n down in front. Property of logs. So here we are. ln y equals n ln 1 plus 2 over n. See, now I'm going to play the same trick as I did over here. Okay, multiplying by n is dividing by 1 over n. Okay, so right now I have ln of y is n, there it is, divided by 1 over n on the bottom, and ln 1 plus 2 over n. Okay, then I take the limit as n approaches infinity of both sides. Okay, if two things are equal, the limit as n approaches infinity of both of them are equal. Only tricky thing here is when I get this answer, I'm not finished. I found the limit as n approaches infinity of ln y. Ultimately, I'm trying to find the limit as n approaches infinity of y. Okay, I would have found it for ln y. So to get rid of the ln, I would have to exponentiate my answer. Okay. So one more time, I'm trying to find limit as n approaches infinity of y. I'm going to have ln y. So after I find the limit, I exponentiate. Okay, so play the same game as before. This is 0 over 0. When n gets big, 1 over big is 0. 2 over big is 0. 1 plus 0 is 1. ln of 1 is 0. So it is 0 over 0. Okay, think of 2 over n as 2n to the negative 1. So I do L'Hopital's rule. The derivative of the top is 1 over 1 plus 2 to the n. And then by the chain rule times the derivative of the inside. So I have to differentiate this. Derivative of 1 is 0. Derivative of 2n to the minus 1 is negative 2n to the negative 2. Okay, at the bottom, 1 over n treated as n to the negative 1. Its derivative is negative n to the negative 2. And then negative 2 cancels out. Double negative makes it a positive. Sneak the 2 up there. So I have limit as n approaches infinity of 2 divided by 1 plus 2 over n. That comes out to be 2. Okay, so looking back over here, limit as n approaches infinity of ln y is now 2. Limit as n approaches infinity of ln y is 2. But I'm trying to find the limit as n approaches infinity of just y, so I exponentiate. Put an e here, e and ln will cancel out. So I have what I want. So the limit as n approaches infinity of y is e squared. Okay, so the final answer is just e squared. Okay, then my 55, let's see if it's the same thing. Yeah, I think it's the same thing. N factorial over 2 to the n. So what's happening? Let me write some of the terms out. 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, right? 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. Okay, can you see what's happening? The top is winning. All right? As I keep going term after term, the bottom you keep multiplying by 2, but the top you keep multiplying by a bigger and bigger number. Right? After here. See, take a look at this. 1 times 2, 2 times 2. What happened here? I multiplied the top by 3, the bottom by 2. So the top got bigger. Now look at the next one. 1, 2, 3, 2, 2, 2. I multiply the top by 4, the bottom by 2. Next one, multiply the top by 5, the bottom by 2. So the bottom you keep multiplying by 2, but the top bigger and bigger, so the limit is infinity. Or we can say that the sequence diverges. Okay, again, here's my abbreviation. I'll use C for converge, D for diverge. Okay, so for the problems at the end, 72 through 78, show you the directions. The problems might not match, but just the idea. Increasing, decreasing, or not monotonic. So not monotonic means sometimes it goes up, sometimes it goes down. Is the sequence bounded? So increasing, we know what that means. It's always going up. Decreasing, it always goes down. Okay, either increasing or decreasing is considered monotonic. So if it goes up and then it goes down, it's not monotonic. Then it asks if the sequence is bounded. Okay. And I'm seeing some of mine do not match some of yours, but that's okay. Okay, 72. A sub n is -2 to the n plus 1. Okay, sometimes write some of the first few terms out to get a feel of it. So I plug in 1, -2 squared. Plug in 2, -2 cubed. -2 to the 4th power. -2 to the 5th power. 4, -8, 16, -32. Okay, so this is not monotonic. It alternates plus, minus, so it goes up, down, up, down, up, down. In fact, the amount that it goes up and down is bigger and bigger. And this sequence is definitely not bounded. You can get as big as you want. You can get as low as you want. There's no one number that I can say is bigger than all of these. There's no one number that I can say is smaller than all of these. Okay, so it's not bounded. Okay, 74. A sub n, 2n minus 3 over 3n plus 4. Plug in 1, -1 over 7. Plug in 2, 2 times 2 minus 3 is 1. 3 times 2 is 6, plus 4 is 10. Plug in 3, 2 times 3 is 6, 6 minus 3 is 3. Plug in 3, 3 times 3 is 9, 9 plus 4 is 13. Plug in 4, 5 over 16. Plug in 5, 7 over 19, and so on. Okay, so if you look at the pattern, it does seem to be increasing, right? It does get bigger. Well, negative to positive is already bigger. This is like 0.1. This is 0.2 something. And it does get bigger, so it's increasing. Is it bounded? Yes. Okay. Is it bounded below? Well, yeah. All the numbers are greater than or equal to -1/7. Even though this is increasing, you can tell by the pattern, well, when n gets super big, you can tell the limit's going to be 2/3. So I don't have a hold of this exactly, but all the numbers should definitely be less than or equal to 1. So I would say 1 is an upper bound. So this is a bounded sequence. Okay, there's a number that's bounded below, like -1/7. And by the way, if I say -1/7 is a lower bound, you can pick any number lower than that, like -10 or -1,000,000. That qualifies as a lower bound. All the terms are greater than or equal to -1,000,000. And an upper bound seems to be 1. But if I have an upper bound, anything above that is an upper bound also. 2 is an upper bound. Pi is an upper bound. 80 is an upper bound, right? In this particular case. Okay, 76. A sub n is n e to the -n. I'm going to write it as n over e to the n. Okay, plug in 1, 1 over e. 2, 2 over e squared. 3 over e cubed. 4 over e to the 4th, and so on. Okay, these are decreasing. Okay, you might not be able to tell, but the argument is the top you keep adding 1. right? The bottom you keep multiplying by e. So even though you keep adding 1, that doesn't have as much of an effect as if you keep multiplying by e. So it is going to be decreasing. Or you can punch this in a calculator, right? You can see it's going to be decreasing. It is bounded. So the biggest number is 1 over e, because these will all get smaller. But a lower bound would be 0, right? In fact, that would be the limit. As n approaches infinity, we seem to be approaching 0. So that's that, decreasing and bounded. Okay, and then finally, my 78, and unfortunately, I'm noticing these aren't matching yours, but be that as it may. Okay, and by the way, after this, I'll be done. Okay, so we're going to break, and then after the break, I'll let you ask questions for as long as you want. Okay, if we end quote unquote too early, then maybe I'll sneak in a little bit of 11.2 just in case something goes wrong later, but I'll still let you out early somewhat. So my formal lecture today is done pretty soon. It's only about 8 o'clock, so I'll be done shortly. Okay, so after the break, Q&A section, question and answers. But if there aren't that many, I'll sneak in some of 11.2. Okay, A sub n is n plus 1 over n. So that's 1 plus 1 over 1, 2 plus 1 over 2, 3 plus 1 over 3, 3 and a third, 4 and 1/4, 5 and 1/5, and so on. Okay, it's clearly increasing, but you can tell it's not bounded. This can clearly get as big as you want, right? 6, 7, eventually a million, a billion, a trillion. So this is not bounded, okay, but we will say it's bounded below. There is a lower bound, 2, which also means 1 or 0 or -1 or -1 million. They would be lower bounds. There's no upper bound to this sequence. Okay, folks, I'm done with section 11.1. Okay, so start thinking of your questions in preparation for the test after the break. I'm still going to let you have a Q&A session Tuesday, but again, the more we do tonight, the less we have to worry about next time. Okay, now I don't have to start any of 11.2 if you ask questions the rest of the time, but if you don't, I'm not just going to stop. I don't want to waste time completely. If I have a chance to get ahead, I'll get ahead in case something goes wrong, so to speak, again. Okay. All right, so I'm done with 11.1. I will stop the share. Let me check the chat. Nothing in the chat. Okay, so we will break 8:15. Okay, so 8:15. Think of your questions from chapter 10 for review. And if not, then I'll just continue on. Okay, so break time. Okay, folks, we're going to start up again. All right, so I will let you ask questions for as long or as short as you wish, and then figure out how much I want to do after that based on what you have. Okay, so anything from chapter 10. Remember to bring your polar graph paper next time, of course. Usual rules for exams, as you know. So I'll lecture the first half, then second half, I'll send via Canvas announcements the exam, but I also project it for all of you too. Okay. All right, so you can either unmute yourselves or you can put it in the chat for any questions for chapter 10. So
I have one.
Okay.
10.4. No, 10.4. 10.2. Number 19.
10.2, number 19.
Mm-hmm.
10.2, 19. Okay, let's see, 10.1, number 19. So yeah, to be safe, bring 2 pieces of polar graph paper. You'll definitely have to graph one, okay, but have a second one in case you mess up, I suppose is the way to say it. Okay, so I have 2 questions so far, 10.119, 10.219. I don't see anything else. Remember, the more we do tonight, the less we have to do Tuesday, and so you can have more time for the test. But we'll see.
Taking up all this damn.
10.1, 10.1, question 3. 10.2, number 9. Okay. And okay, that's 4 questions. So let me start with that. And I can't see the chat at the same time as sharing the screen. So you can go ahead and still put stuff in the chat, but I won't be able to see it in the meantime. Okay. So let me get organized here and see what I got. Okay. Oh, I saw one more. 10.363, it looks like. Okay, so go back to sharing the screen. Okay, so maybe I'll just go in order of the sections. 10.1. 10.1, number 3. 10.1, number 3. X is equal to t plus sine of t. Y equals cosine t. T between negative pi and pi. Sketch the curve and indicate with an arrow the direction of increasing t. Okay. So t, x, y. Going from negative pi to pi. So how about negative pi over 2, 0, positive pi over 2, pi. Okay, sine of pi is 0, sine of 0 is 0, sine of pi is 0, so I'll just have negative pi, but I'm going to have to graph it. It's negative 3.1. Sine of negative pi over 2 is negative 1. Negative 1 minus pi over 2, negative 1.57, so negative 2.6 roughly. 0, 0. Pi, sine of pi is 0, so pi gives me pi, or 3.14, 3.1 call it. Pi over 2, sine of pi over 2 is 1, so 1 plus pi over 2, 1 plus 1.57, 2.57, call it 2.6. Okay, cosine of negative pi, negative 1, 0, 1, 0, negative 1. Okay, then I just plot x versus y. So how far do I have to go? Just a little bit more than 3. I might as well just plot 3 and just go a little bit farther. One, two, three. 1, 2, 3. And this one, I only have to go 1 and -1. So there we go. So -3.1, -1, -2.6, 0, 0, 1, 2.60, 3.1, -1, something like that. So it's going this way. All right. Okay, then what do we have? 10.119. X equals 5 plus 2 cosine pi t y is equal to 3 plus 2 sine pi t. T is between 1 and 2. First, let's see if we can get a good description of what this thing looks like. Since I have a cosine and a sine, let's try to force there to be a cosine squared plus sine squared equals 1. So x minus 5 divided by 2 is cosine pi t. Y minus 3 divided by 2 is sine pi t. Square them. X minus 5 over 2 squared plus y minus 3 over 2 squared is cosine squared pi t plus sine squared pi t, which is equal to 1. That's how you would eliminate the parameter when you have a cosine and a sine typically. Right? Force the equation to have cosine squared plus sine squared equals 1. Okay, so getting back over here, I've got that equals that. Let me multiply both sides by 4. That eliminates that and puts the 4 over there. So x minus 5 squared plus y minus 3 squared equals 4. So that's a circle centered at 5, 3, and a radius of 2. Okay, so I know what that's like, but let me see what actually happens in this case. Okay, so one more time. I force it to look like cosine squared plus I squared, sine squared. So isolate the cosine pi t, subtract 5, divide 2. Isolate sine pi t, subtract 3, divide 2. Square both sides, so you get cosine squared pi t plus sine squared pi t equals 1. And then get this to be more recognizable. The denominators of both of them are 4, so multiply both sides by 4, and we have that. Okay, so let me go ahead and draw this circle centered at 5, 3, radius 2. Okay, so let's go with that. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Center is 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. And the radius is 2, so 2 to the left, 2 to the right, 2 up, and 2 down. So that's the whole thing. But now let's analyze this a little further. Okay, so let me rewrite here. X equals 5 plus 2 cosine pi t. Y equals 3 plus 2 sine pi t. Okay, we're going from 1 to 2. So how about I plug in 1, 1.5, and 2? So t equals 1, t equals 1.5, t equals 2. Okay, so if I plug in 1, okay, plug in 1, cosine of pi is -1, times 2 is -2, 3 comma. Plug in 1, sine of pi is 0, so 3, 3. 1, 2, 3, 1, 2, 3. Okay, so it starts here. So here, t is equal to 1. 1.5. Plug in 1.5. That's like 3 pi over 2. Cosine 3 pi over 2 is 0, so I would have 5 comma something. 1.5 here. Sine of 3 pi over 2, -1. Times 2, -2, plus 3 is 1. 5 comma 1. So t equals 1.5. And I'm pretty sure this is t equals 2. Okay. The way it's going, right? But just to be safe, plug in 2. Cosine of 2 pi is 1. Times 2 is 2, plus 5 is 7. Plug in 2 here. Sine of 2 pi is 0, 7, 3. And that's over here. Okay. So there we go. So describe the motion, it says. Describe the motion. So on the circle, x minus 5 squared plus y minus 3 squared equals 4. Starting at here, where's here? 3, 3. And going, let's see, this direction is counterclockwise. And going counterclockwise to my ending point. Where was my ending point? 7, 3. So that's a description of the motion of this particle. Okay. Okay, then 10.2. Ten 9 and 19. (10.29) x equals t squared minus t. Y is equal to t squared plus t plus 1. The point is 0, 3. Find the equation of the tangent to the curve at the given point. Okay, never mind about the graph. It's too complicated. Graph to curve is tangent. Okay, so we're at the point 0, 3. So first I have to figure out what the t is. So put 0 here and 3 here. 0 equals t squared minus t, which is t times t minus 1. That is t equals 0 or t equals 1. But t equals 0 doesn't make this equal to 3. But t equals 1 makes it equals 3. So we have t equal to 1. Okay, so one more time, how do I do that? That has to be 0. That has to be 3. If I put a 0 here, solve, t can be either 0 or 1. But if I plug in 0 here, 0 plus 1 doesn't come out to be 3. So I have to eliminate that possibility. T equals 1, that works. 1 plus 1 plus 1 is 3. So t is equal to 1. Okay, then dy dx by formula, dy dt divided by dx dt. Put that on your cheat sheet. So dy dt 2t plus 1. Dx dt 2t minus 1. Now I plug in 1. At t equals 1, dy dx is 2 plus 1 divided by 2 minus 1, 1 over 3. Okay, point, slope. So y minus y1 equals m times x minus x1. Okay, and then 10.219. 219. X equals cosine theta. Y equals cosine 3 theta. Tangent line is horizontal or vertical. Okay, dy dx, dy d theta divided by dx d theta. So dy d theta is sine 3 theta times 3. Dx d theta is, oops, should be a minus. Yeah, and this is negative sine theta. Negatives cancel out, so 3 sine 3 theta over sine theta. Okay, now horizontal tangent means the top is 0, but at the same time the bottom cannot be 0. 3 sine 3 theta equals 0. Sine of 3 theta equals 0. So if I just look at sine of what equals 0, 3 theta is a multiple of pi. K pi, where k is an integer, divide by 3, divide by 3. So theta is k pi over 3, where k is an integer. Okay, but we have to watch out for points where the denominator is also 0. Okay, so that eliminates, I might as well do sine of theta equals 0. Theta is equal to k pi, where k is an integer. Okay, so that means I don't want k to be 0, 3, 6, 9, and so on. Okay, so horizontal tangent, theta is k pi over 3. Now, the easiest way for me to say this right now is 1, 2, but not 3, 4, 5, but not 6, 7, 8, and so on. And that could be plus or minus. It's kind of a funny way of saying it. Okay, but if I go all the way for 1 revolution, okay, and these are supposed to be, no, I guess they're not polar, since this was before polar coordinates. But anyway, we'll just go with that. Let me double check again. Points on the curve. Okay, so this is not polar coordinates yet. Technically. All right, so as ordered pairs, see, theta is pi over 3. Cosine of pi over 3 is 1/2. And that would be cosine of pi, so 1/2 -1. Theta is 2 pi over 3. That would be -1/2. And then, yeah, it looks like we have nothing new after that. So we don't want 3 pi over 3 and so on. Okay, so I'm going to say this is all we need. So if I keep going all the way around, I'm just going to get a repetition because of the periodic. These are both periodic functions. Okay, so 1/2 -1, -1/2, 1, looks like. Okay, so again, I'm not doing 3 pi over 3 because that makes the top and the bottom 0. Okay, so I'm not going to declare any vertical tangents for this particular one. Okay, 4 pi over 3. Let's see what happens at 4 pi over 3. Pi over 3. Cosine of 4 pi over 3. -1/2. Put 4 pi over 3 here. Cosine of 4 pi, that's also 1. So we already got that. So there's nothing new. Okay. So it looks like this is all I'm going to say for horizontal tangent. And vertical tangent, well, if I set this equal to 0, I get k pi, but that also makes this equal to 0. So in other words, the numerator. So the same spots where the denominator is 0, which are going to be 0 plus or minus pi plus or minus 2 pi, the top would also be 0. Okay. So I'm going to say no vertical tangents. Okay. So just 1/2 -1 and -1/2, comma 1. And that's it for that one. Okay, and then we have 10.363. Horizontal or vertical tangent again. R equals 1 plus cosine theta. Okay, so I have to plug into this thing. And again, put that directly on your cheat sheet. Dy dx is dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. And again, I think it asks for horizontal or vertical tangents. Yeah. Okay, so dr d theta is negative sine theta. So negative sine theta, negative sine theta. This one is times sine theta. This one is times cosine theta. Plus, minus r, so the original r, 1 plus cosine theta, 1 plus cosine theta. And this one gets cosine theta. This one gets sine theta. Okay, so let's clean it up. Negative sine squared theta plus cosine theta plus cosine squared theta divided by negative sine theta cosine theta minus sine theta minus sine theta cosine theta. So the bottom is 2. Looks like 2 negatives, right? So negative sine squared theta plus cosine theta plus cosine squared theta over negative 2 sine theta cosine theta minus sine theta. Okay, so horizontal tangent means the top is 0 and the bottom is not 0. So negative sine squared theta plus cosine theta plus cosine squared theta is equal to 0. Let's change everything to one trig function like cosine. So negative sine squared is 1 minus cosine squared theta. Okay. This is off the identity sine squared plus cosine squared equals 1. That means sine squared is 1 minus cosine squared. And likewise, cosine squared is 1 minus sine squared. Plus cosine theta plus cosine squared theta equals 0. So now this is one trig function. Okay, let me see if I can do this all at one fell swoop. I've got positive cosine squared, right? Another cosine squared, so 2 cosine squared theta plus cosine theta minus 1 equals 0, like that. I think that's right. Paren, 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 paren. 2 cosine theta, 1, 1. Let's see, how do you end up with a positive? Like that and like that. So that means this is 0 or this is 0. 2 cosine theta minus 1 equals 0. Or cosine theta plus 1 equals 0. Cosine theta is 1/2. Or cosine theta equals negative 1. Okay, so unit circle. Cosine's x coordinate. X coordinate is 1/2. Go like that. So that's there and there. Pi over 3. And, well, negative pi over 3 or 5 pi over 3. Let me go negative pi over 3. Cosine of theta is negative 1. That's over here. Pi. Okay, but let me check over here. Does pi make any of these 0? Yes. Sine of pi is 0. Okay, so that's eliminated. Pi over 3, the denominator is not 0. Negative pi over 3, the denominator is not 0 either. Okay, so I have pi over 3 and negative pi over 3. Okay, they want us to list it as points. So I plug into here. Cosine of pi over 3 is 1/2. So I have pi over 3, negative pi over 3. And cosine of pi over 3, cosine of negative pi over 3 is 1/2. So let's see. So if I plug in either of those, I get 3 over 2. And are these 180 degrees apart? No, they're not. Okay, so this is my answer for horizontal tangent. Okay, so again, I have to eliminate this because both the top and the bottom are 0. Okay, then for vertical tangent, set the denominator equal to 0. So vertical tangent -2 sine theta cosine theta minus sine theta equals 0. Factor out -2, whoops, sorry, not negative, just negative sine theta. So what that'll give me 2 cosine theta plus 1 equals 0. Sine of theta equals 0, or cosine theta is -1/2. Unit circle, sine of what angle is 0? 0 and pi. Cosine of theta is -1/2. X coordinate is -1/2. That angle and that angle. 120 degrees, 2 pi over 3, and 4 pi over 3. But again, I have to watch out. Okay, I think we already eliminated pi. Pi was no good. Okay, let's try 0. If I plug in 0 to the numerator, do I get 0? So put a 0 in the numerator. We're good. 2 pi over 3 in the numerator. It doesn't look like it's going to give me 0. Okay. So theta is 0. 2 pi over 3. 4 pi over 3. Write them as points. 0, 2 pi over 3, 4 pi over 3. Okay. Plug in 0. Cosine of 0 is 1. 1 plus 1 is 2. 2 pi over 3, well, 2 pi over 3 and 4 pi over 3, we already know cosine is -1/2. So -1/2 plus 1 is 1/2. All right, so that's what I'm going with for vertical tangents. So vertical tangents, horizontal tangents are these two, looks like. Okay, and I think I'm caught up. So let me stop sharing and check the chat. Okay. Okay, let's see. 10.1, 15, 10.3, 45, and 59. And if you ask a question and I don't get to it, ask again, because with so many things going on, sometimes I might miss a question or I miss something from the chat if I don't scroll down or whatever. 10.1, 15, 10.3, 45, and 59. Okay, so I think I'm caught up again. You can go ahead and put stuff in the chat again, but I won't be able to see it until I'm done again. So let's go back. Okay, 10.115. All right, let's see what that's about. X equals t squared, y equals ln t. Eliminate the parameter to find a Cartesian equation of the curve. Sketch the curve and indicate with an arrow the direction in which the curve is traced as the parameter increases. Okay, so let's eliminate the variable. So I have to solve for t either here or here. If I solve for t here, I'd have to include a plus or minus. I don't want to do that. So let me solve for t here. I can exponentiate. Whoops, like that. So t is equal to e to the y. And plug that into here. So x is equal to e to the y squared, or x is equal to e to the 2y. That's true, but we're more comfortable with y as a function of x. So let me take the natural log of both sides. Ln x equals ln e to the 2y, which equals 2y. So y is equal to 1/2 ln x. Okay. So we should be more comfortable with that. Okay, so how does 1/2 ln x compare to ln x? It has the same general shape. It just doesn't go up as high, but it still will look like so. Why shouldn't I put the arrows? Because I'm supposed to put the arrow direction of increasing t. Okay, so how do I do that? Oh, how about I just plug in some stuff? Okay, so when t equals 1, x is 1, right? And when t equals 2, x is 4. So here's 1, here's 4. Okay, so that means it's going this way. See what I did? I didn't even have to worry about the y value. Okay, increase t. So I plug in 1, 1. Plug in 2, 4. So here's x equals 1, here's x equals 4. So it's going that way. Okay, then let's see, 10.3, 45, and 59. Yeah, I'll have to use this. 10.345 is a polar graph. So I will have to get one of my polar graph papers. I only have about 4 left. So if you ask me to do more than 4, I won't be able to do it right now. 10.345, or maybe should I do 59 first? Yeah, let me do 59, then I'll come back. Hmm. 10.359. R equals, oops, cosine 2 theta. R equals cosine 2 theta. Theta is pi over 4. Find the slope of the tangent line to the given polar curve at the point specified by the value of theta. Okay, so dy dx, I'm using this thing again. So dr d theta, negative sine 2 theta times 2. Negative 2 sine 2 theta, negative 2 sine 2 theta. Multiply the top by sine, bottom by cosine. Top's a plus, bottom's a minus. R, so I just copy cosine 2 theta. And then cosine theta, sine theta. Okay, and I'll just plug in. Okay, so let's see. Plug in pi over 4. On top, negative 2. Sine of double the angle, sine of pi over 2 is 1. Sine of theta, sine of pi over 4, radical 2 over 2. Plus, oh, I might as well, yeah, I might as well just copy this. Negative 2 times 1, that's not going to change, right? Okay, cosine 2 theta, cosine of pi over 2, 0. So I don't care what this is, that's 0, that's nice. Cosine of pi over 4, root 2 over 2. So the top equals the bottom, so the answer is just 1. It didn't come out so bad after all, unless I made a mistake. But it looks to me like the answer is 1. Okay, 10.345. R equals sine of theta over 2. And I think that's the only instance where instead of doubling the angle or tripling the angle, you have a fraction of an angle. Okay. So let me use one of these guys. R equals sine theta over 2. That. And yeah, let me check something here real quickly. Sorry about that. Okay, so for this one, what you actually need to do is you pick your angles like 90 degrees and so on, but I have to go around twice, so to speak. Okay, because if I plug in 90, I'm taking the sine of 45 degrees. Okay. That's opposite of what I did. Let's say if I have 3 theta, I would go 45 divided by 3 is 15 degrees. Here I'm going to plug in, let's say, 90 degrees, because if I plug in 90, I'll get 90 divided by 2, which is 45. Okay. So I'm not going to be able to go all the way around until I get to 720 degrees. See, the period's 4 pi. So I need to go all the way out to 4 pi this time. Okay. So the maximum R is 1. So 10th circle. Okay, so 1 circle is 0.1. Okay, that's not too bad, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And go like this. Okay, so 0, 2 pi, 4 pi. Okay, see if I plug in 90 degrees, I'll be doing sine of 45 degrees. Okay, so I want here, so pi over 2, which is also 5 pi over 2. This is pi and 3 pi, 3 pi over 2, and 7 pi over 2. So I'm going basically pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, that's a 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, which is 4 pi. The period of this function from trig is 4 pi. The formula being 2 pi divided by b, 2 pi divided by half, 4 pi. Okay, so my chart's going to be like so, or theta. So again, I'm going to put every 90 degrees, because if I plug in 90, 90 divided by 2 is 45, so I'll be getting the 45 degree mark that I had anticipated. Okay, so pi over 2, pi, 3 pi over 2, 2 pi. Keep going. 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Okay. R equals sine theta over 2. Okay, plug in 0, 0, and 0 at the end. And 2 pi divided by 2 is pi, sine of pi is 0. Plug in pi, sine of pi over 2 is 1. Oops, I put this in the wrong spot. That should be 0. At that aim. 3 pi, sine of 3 pi over 2, negative 1. Okay, half of pi over 2 is pi over 4. These are going to be radical 2 over 2, 0.7 or negative 0.7. So that looks like 0.7, 0.7, negative 0.7, negative 0.7. Okay, so 0, 0. Okay, I really should put in 45-degree marks because it doesn't just go straight there in a straight line. Okay, so if I were to go 45 degrees, sine of 22.5 degrees, it is a positive quantity, so it does curve over there. But pi over 2 comes to 0.7. 1, 2, 3, 4, 5, 6, 7. Something like that. Then by the time I reach pi, it's at 1. Kind of grows out to there. And then what? 3 pi over 2, 0.7 again. 7th circle. And then 2 pi back into 0. And then 5 pi over 2, which aims here, it's negative 0.7. So it curls back on itself like this. 3 pi is over here, but negative 1. So it curves back over like that. And 7 pi over 2, you're aiming down, but the negative 1 means I'm going back over here. And then I come back into 0. So very unusual. So it looks like that. Okay, that's 45. And so I can't show you the whole picture at the same time, so I have to do it in pieces. We're still recording, so hopefully you can still see that. And that. And the table. Okay. All right, so that's that, and I think I'm caught up again. Okay, so let me stop the share. And what else do we have? Okay, can I solve for x equals t squared? Yeah, so the problem with question 15 on 10.1, go back to that. That's not as good because technically you'd have to do a plus or minus. So that's again. Okay, I solve for t here. Can I solve for t here? When you do the square root, you'd have to have a plus or minus. And you usually want to avoid plus or minuses. Okay, you don't have no such worry here. So that's why in this particular case, it probably would have been better to go that route. That's all. Okay. Stop the share there. Okay, and I think I'm caught up. What time is it? 9:06. All right, so yeah, I don't think I want to do any more lecture today at this stage. Okay, so anybody else with a question, please? Otherwise, we'll call it a night. Okay, I don't hear anything. So Tuesday, I will start section 11.2. Then again, questions and answers, break, and then we take our test and you have your homework ready. There's that 70% rule, but I end up doing a lot of problems. What was, I think section 5, didn't I literally do just about every problem? So it should not be that hard to do the 70% homework rule, considering I do a great percentage anyway. Okay, so no quiz today, or there is a quiz and everybody gets a 5, all right? So how do you like that? Okay, so I think that's about it, folks. So we're done. Have a good night. So prepare for the test next Tuesday. I'll lecture first, let you ask questions, and then test, all right? Okay, that's it for tonight, folks. So have a good evening. Bye, everyone.
Bye, Mr. Hom. Good night.
Good night.